Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. Now we have our complete schematic. Well, almost. Yes, all of the connections are defined and the component symbols are in there, but there is something missing. Now remember that one of the characteristics of a component in a schematic capture is the very physical entity known as the PCB pattern or footprint. This is what defines how this component will be connected on the PC board. Before we can dive into laying out our board, we have to make sure that all of our components have a PCB pattern. Now I know for certain that in this mixer design that we're working on here, 3 components do not have a PCB pattern assigned to them. There is the itsy bitsy teeny weeny little potentiometer used to adjust the LED trip point for the output level indicator. There are all of the level potentiometers. There are 4 of those. And then finally the DC to DC converter that I chose for the power supply. Now, I'm not going to go through the whole process of creating all 3 of these footprints in this video. I will choose the DC to DC converter as a representative device and create its footprint in detail for you. Now, because the major difference between surface mount footprints and through-hole footprints lay in the definition of the pads or pins for the device, I will show you how to create through-hole pads for your PCB pattern. The placement of the created pad is no different than what we would do for surface mount footprints. And then finally, I will show you how to percolate the newly created patterns all the way up to the schematic so that you can design your PC board. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, on to the first steps. Before we can create anything, we have to know what we're going to be creating, and well, who better to know this than the folks that make the thing? Oftentimes the manufacturer provides a suggested PCB footprint for you. All you have to do is follow what they tell you. Thus, the very first part of this process is finding the datasheet or mechanical drawing of the part as provided by the manufacturer. These very often will be in the datasheet, usually toward the end of it. Sometimes these are in separate drawings that can be downloaded from the manufacturer's website. In the end, wherever we get it from, we need that drawing. They will tell you the size of the pads that are needed, the diameters of the holes, the spacing between the pins and the pads, and the size of the body of the part, and well, a whole bunch more. Unfortunately, most of the time the dimensions they provide don't just slide into the stuff that we need to create the footprint. We have to do some math to figure this stuff out. So I've pulled the data sheet for the DC to DC converter, so let's start our planning. The first thing that we have to remember is that the coordinate x equals 0, y 0 point for most parts should reside at the geometric center of the part. Now you'll notice right away that this is not reflected in the dimensions given in the data sheet for the DC to DC converter. So what is it that we need to know? We need to know the size of the pads. In other words, the length and the width of the pads. Now with some parts, there could be some pads that are required to be different sizes than others. And I'll talk about how to do that a little bit later in this video. We need to know the position of the pads in both the X and the Y direction. Now remember, their position in this software is relative to the geometric center of the pad, not the edges of the pad. Thirdly, we need the outline of the actual body of the component, its dimensions. As you can see from this drawing, they give you all sorts of dimensions that you can use to determine all of this stuff. But they really don't give you what you need the way you need it, and this is a very common thing to discover. Now, I'm not going to walk through the machinations necessary to determine them, as, well, this is a relatively simple mechanical exercise. But I did go through them, and I found out exactly the size of the pads. I found the position of each of the 5 of the pads, and then I got the size of the body. And now that we know what we're going to create, let's go create it. The first thing we have to do is open the pattern editor. Well, that was easy. We navigate to the User Patterns group by clicking on the arrow on the right side of the group field and clicking on the User's Pattern group. If you're new to DipTrace, then the list of pattern libraries will be empty. For the sake of this video, I am going to play like this is the case. We have to create a new pattern library. Right-click in the Library selection field and select New Library from the pop-up menu. Enter the library name in the Name field of the dialog box. I will create one called Demo. Optionally, you could also enter a description of sorts in the Hint field. Click on the OK button. A new untitled pattern now exists in this library. This is the one that we're going to use for our part. Now we have to enter the pattern properties. In the Pattern Properties dialog box, enter the name for this pattern. Now remember, this is going to be the searchable name that appears in the various search fields. In our case, this pattern will work for any of the parts in the PQP1-M series of DC to DC converters from CUI Incorporated, so this is the name I'm going to give it. In the Ref Des field, we enter the reference designator prefix associated with this part. This is like R for resistor, L for inductor, U for integrated circuits. And because this DC to DC converter is very integrated circuitish in nature, I will enter U here. We can enter a value in the Value field, because this is for the entire PQP1-M series. This is what I will put in here. I will put CUI, Inc. in the manufacturer field, as they're the ones that make the part. The entry in the datasheet field could be a link to the datasheet for the device. This can point to an internet source or a local repository. I'm going to leave this blank for now. Now we get to start putting in the specifics for the footprint. We begin this with what is called the standard pad properties. Standard pad properties define what is standard for the part. We define the pads that will have the characteristics of the majority of the pads in the footprint. We click on the Standard Pad Properties button. Keeping it simple, this is a surface mount pad, which will be a rectangle. Per what we gleaned from the datasheet, its width is 4.5 millimeters and its height is 1 millimeter. Click on the OK button. Now we're ready to build the footprint. We need to locate a total of 5 pads. Now the easiest way to do this is to randomly place 5 pads and then edit their specifics in the editor. This way stuff gets exactly where they're supposed to be. I click on the Place Pad icon in the toolbar. Now, everywhere I click drops a pad. I pick 5 spots and drop 5 pads. Then right-click to get out of the Place Pads mode. Unfortunately, the specifics of the pads have to be edited 1 pad at a time. Right-click on the pad and click on the Pad Properties in the pop-up menu. Now, we edit its information in the dialog box. Number is the pin number, so pin 1 is number 1. This is what the component editor looks at to match up component pins and pattern pins, and these need to match the pin numbers of the schematic component. Now we enter the X and Y coordinates for the pad in the position section. We determined that our pin 1 is at X equals minus 5.75 millimeters and Y is at plus 3.81 millimeters with a pad angle of 0 degrees. So I enter that here. Now we click on the OK button. You will notice that the pad has now moved to its new position in the footprint. I'm going to repeat this process for each of the rest of the pads. Now, let's place the component outline. There are 2 levels of outline that we have to place. The first is in the silk screen for component placement. The second is for the assembly drawing. Now, in many cases, these are going to be the same, but you could add all sorts of nice features to the assembly drawing to prettify the drawing. In our case, with this component, a simple box will suffice. Our first step is to select the layer that we're going to want this on. Notice the drawing tools in the upper left-hand corner of the screen. Just to the right of them is a drop-down box which allows you to choose where the drawing item is going to go. I will choose the top silk layer. There are filled and non-filled shapes. For the sake of the silk screen, the non-filled shapes are the choice. I click on the non-filled box shape tool. You draw this by defining the 2 opposite corners of the box. Now, we could very carefully position things to do this, or we could just do the whole random drop and define the thing again. I prefer the random drop and edit option. I click and hold at the top left corner and then drag down to the lower right corner. When I release the mouse button, the box is drawn. Now I need to edit its size and its position. I right-click or hit Escape to exit Place Rectangle mode. Now I right-click on the rectangle and select Properties from the pop-up menu. Notice at the top of the dialog box that we can choose the layer that the box will live on. I will leverage this a little bit later. We set the anchor point at X equals 0 and Y equals 0, which is at its geometric center. Now, all we have to do is enter the dimensions of the box, and well, it'll be there. The width, in other words, the X dimension, and the height, the Y dimension, are both 14 millimeters for our part. Now that I've entered these, I click on the OK button. You can see that our box not only changed size, but also position. Well, now for the assembly layer. Right-click on the box and choose Copy from the pop-up menu. Now click anywhere else in the window and then right-click and choose Paste from the pop-up menu. Right-click on the copy of the box and click on the Properties from the pop-up menu. Change the layer to Top Assembly and the anchor point to X equals 0 and Y equals 0. Click on the OK button. Now our box is sitting right in the perfect place. Now we have one last thing to do. Don't forget your reference marks. Yes, we want to place a reference mark next to pin 1 so that the orientation of the part is clear. While it is very obvious with this part, there are a lot of parts that require this, such as, well, polarized capacitors, diodes, integrated circuits that have symmetrical pins. I'm going to use a filled circle for this one. I make sure that the top silk layer is selected. I click on the filled around icon in the toolbar And then, like the box, we click and drag to draw our little filled circle. Our part is now complete. Let's save our database. You'd think that the fact that we gave the library a name would also define the library file name, but it doesn't. Give it a name and click on the Save button. Now, let's turn our attention to a through-hole part. We begin by right-clicking in the Parts library and selecting Add a new pattern to the Demo Library option in the pop-up menu. We now have a new untitled part in the library. We follow all of the same steps with this through-hole part that we did with the surface mount part, defining the name and the reference designator and the value and the manufacturer and all that stuff. Where we really differ is when we define the standard pad properties. So let's click on that and see what I mean. We select through-hole from the type options and we're faced with a whole host of things to look at. The most important things to be concerned with are the pad shape, the pad size, and the hole diameter. The difference between the hole diameter and the pad size constitutes the annular ring of the pad. The annular ring is the copper that we see around the hole and is what we solder stuff to. This must be large enough to accommodate a nice solder fillet around the pin or wire after it has been soldered into place. The other aspect of this requirement is the accuracy of the drilling operation. The drilling is not perfect, and it is very, very rare for it to hit the exact center of the pad. The size of the pad has to be such that the hole drilled will never escape the copper pad it's associated with. To accommodate variances in drilling accuracy, hole plating, we have to establish a minimum pad size. And I emphasize that this is a minimum size. Now, we can make the pad larger if we want. As a general rule, the absolute minimum pad size will be the hole size plus 10 mils or 0.25 millimeters. This is a minimum and is most often larger than this for things like resistors and ICs and capacitors and transistors and the like in order to allow for a nice solder fillet around the pin. Let's walk through all of this one thing at a time. The first thing I will address is the hole parameters. In most every case, this is going to have a round shape. The center of the drill hole is placed at the reference point of the defined pad. You can see here that it could also be ob-round. Oh, what on earth is ob-round? The easiest way to picture this is a slot with rounded ends. You define the width, which is the dimension in the x direction, and the height, which is the dimension in the y direction. The defined ob-round slot is automatically placed so its geometric center is the reference point of the defined pad. Now, let's talk about those fields that define the copper pad itself. The shape field defines the shape of the pad. Now, there are lots of options here. Most often, we will use ob-round or rectangle. We use ob-round to produce round pads. We just set the x and the y dimensions the same. We use rectangle to create square pads, again with the x and y dimensions the same. Width defines the x-axis outside dimension of the pad. Height defines the y-axis outside dimension of the pad. Unless otherwise specified, the geometric center of the defined pad will be at the reference point of the overall pad. When defining a rectangular pad, you can also have the option of having the corners of the pad rounded. This is defined in the corner radius field. It is defined in terms of percent. Well, what does this percent mean in terms of a pad? Well, picture the rectangular pad. Choose the narrowest dimension of the pad. If we specify 25%, then the corner will be rounded such that it comes down to 1/4 of the shortest dimension. So if my pad is 4 millimeters wide and 10 millimeters long, and I specify 25%, the arc that makes up the rounded corner will come down 1 millimeter on both the long and the short sides of the pad. If I were to specify 50% on a square pad, I would end up with a round pad. If I enter 75%, then your entry would be corrected to 50% because, well, you can't exceed 50% corner radius. Now the last two fields. I did say that the geometric center of the pad will be placed at the reference point of the overall pad of the design unless you specify otherwise. The king of reference point is the drilled hole. The copper pad associated with that drill hole can be moved. In the two offset from hole center fields, we can specify how far we want to move the geometric center of the copper pad itself away from the overall pad design reference point, which is the geometric center of the hole. There are some cases where this is needed, but the vast majority of the time the copper pad remains quite centered on the drilled hole and the reference point. But what if I need to have more than one kind of pad in my design? We just finished editing the pattern's standard pad properties. This defined the pad specifics for the majority of the pads. Well, maybe we want pin 1 to have a square pad and all the rest be round. Maybe there are mechanical mounting pads for the part that require totally different pads than the electrically connected pins. What do we do then? Well, we place a pad just like we did before. Now we right-click on it and select Pad Properties from the pop-up menu. Instead of clicking on the Pattern's Standard Pad Properties button, we uncheck the Use Pattern's Standard Pad Properties checkbox. Now we can edit all of the pad properties we need to so that we could have a very, very different pad for this part of the footprint. Once you've defined all of the pads for your through-hole part, you can proceed to finish up the footprint just like we did with the surface mount part. Now that we have our footprints defined, how does it find itself into the component that we've placed in our schematic? It doesn't just automatically appear there. The first thing we do is save our PCB library. Unless we have a reason to keep it open, we can close the pattern editor. Now there are two ways to proceed from here. Depending upon what you're doing, either of these is the right way to go. Let's talk about the first, where we have defined a component in the component editor, and it's just awaiting a PCB pattern to go along with this library part. This is kind of a global thing, as this defined pattern will follow the component into any schematic we place it in. We open the component editor so that we can attach this PCB pattern to the part. My part lives in the user component group, so I select that. In the user component group, I have a demo parts library where my new component exists. I select the demo parts library, and then the component in that library that I want to assign the new pattern to. In the Components Property dialog box, click on the Pattern button. We are now looking at the Attached Pattern dialog box. Over on the right side, we select the Pattern Library group. My new pattern is in the User Patterns group. Then I choose the Demo Pattern library itself. Finally, I choose the specific pattern in that library that is going to be assigned to our component. I choose the newly created pattern for my DC to DC converter. If the pin numbers of your pattern match the pin numbers of your component like they should, then DipTrace automatically connects everything up for you. I'm quite done, so I click on the OK button. I save the component library and then exit the component editor. But we're not done yet. The schematic still doesn't know anything about this updated component or its associated footprint. We have to open the schematic where this component lives and locate the component. We select all of the components in the schematic that are affected by the change. Here, I select the DC to DC converter in the power supply page. Now, this is the only one of its kind in the design, so, well, this is easy. Click on one of the selected components and hover over the Update from Library item in the pop-up menu. If you have just one group of components, then click on the selected components. If you have a bunch of components in the schematic that are all the same, then you can also click on a Similar Name Components option. There's a caution on this one. If you have 5 places in the schematic where you use the XYZ component and any one of these requires a different footprint than the rest, it too will be assigned the same footprint as all the rest because, well, it has the same XYZ name. In this case, I click on the Selected Components option and, well, I'm done. Now I save the schematic, but what if I don't want to save this on a global scale, such as the generic potentiometer symbol that I placed in the schematic for the level controls and a different one on the LED level adjustment? So we're currently in the schematic, so let's navigate to the level controls in question. First, we select each of the components. Now, I right-click on one of them and select Properties in the pop-up menu. You will now see the Attached Pattern button in the lower left corner of the Component Properties dialog box. Click on this button. Oh, hey, looky here. It looks very, very familiar, doesn't it? We go through the same process of selecting the Pattern Library group, then the Pattern Library, and then the pattern itself to select which pattern is going to be associated with these parts. We might have to edit the pin to pad table for component pin to footprint pad number mapping as necessary. When done, we click on the OK button and then the OK button again. Done and done! Well, don't forget to save the schematic. Well, now that we have defined and assigned all of our PCB patterns or footprints, we're ready to create a PCB design, and that is what the next video is all about. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-oots.